Now for the history of nano. It's commonly regarded as starting with this 1959 talk by Richard Feynman. Of course, chemists would be arguing that they've been making nanostructures for centuries, and they're right. But at least in modern times, this essay had a huge impact. In the book, I argue that probably actually amongst scientists, the things that really kindled the fire was the invention of scanning probe microscopes. But nonetheless, Feynman's essay is remarkable, and it discusses the consequence of these enormous differences between the macro and micro world in a wonderful way, a way that's so good I can't improve on it. So you will find Feynman's essay reprinted in the book as Appendix B. And your homework assignment now is to go and read Appendix B as soon as you have finished with this lecture material. So let's take a quick look at some of the predictions Feynman made, and remembering that these were predictions made in 1959, and look at where we are today. So Feynman was aware of the electron microscope. It had been around for many years already in 1959. And it occurred to him that if you can use the electron microscope to see very small things, you could just run it backwards and take a model of a big thing you wanted to make, an image of a big thing, and project it backwards through the microscope to make a very small image of it. And indeed, that's exactly what is done today in instruments called electron beam lithography instruments. And this picture here is a picture, see the scale bar here is 1 micron, a picture of a device that's been made in a polymer resist for focusing X-rays. It's a Fresnel lens, but a Fresnel lens on the nanometer scale. Another thing Feynman addressed was the problem of, well, gee, we can take an electron microscope and run it backwards to make very small systems, but that's very hard and you've made one of them. What if you want to build a manufacturing economy based on nanostructures? Well, Feynman had an answer there. He said, well, let's go ahead and make one nanostructure, and then let's make a very fine rubber mold and make a copy of it and stamp out copies of this nanostructure. And there is indeed a technology called stamp technology that is available today and beginning to be used quite widely for making nanostructures in many industries. Another Feynman prediction was, well, gee, if you can accelerate electrons through a microscope column and form very small structures that way, couldn't you do the same with ions? Of course, with ions, you carry a lot more momentum because they're more massive than an electron, and so you can knock material out of the surface of a sample. And indeed, there is a machine available today, an ion beam mill, into which you can put a picture, a macroscopic picture of something you want to make, and let the mill work away and demagnify the picture using ion optics as opposed to electron optics. Same thing, just a different sign for the charge. And sure enough, you can make nanoscale structures. So you see this structure here, the scale bar is 3 microns, and the University of Bath logo is here, together with the letters that you see here on the nanometer scale. Here's an example in which a semiconductor device has been cut through using an ion beam mill so that a fault in a transistor could be identified. Then Feynman said, well, we haven't reached the limit with electron microscopy yet, and biology is very complicated, so why don't we just use an electron microscope, but work a little bit on the resolution, and then for biology we can just image where all the atoms are, and then we'll understand living things completely. Well, it turns out that it isn't quite so easy, because the energy of electrons needed to form electron microscope images is quite high, and the beam damage done to soft materials like biological materials is significant. However, scientists have worked out how to operate electron microscope stages at very low temperatures so that biological structures can be preserved at very low beam doses, And then by doing careful diffraction from material on this low temperature stage and reconstructing a three-dimensional image, some quite remarkably complex structures have been solved. The false color structure you're looking at is one section through a three-dimensional structure solved for a material called an epsilon 15 bacteriophage. This is a virus that infects and eats bacteria for a living, and this whole thing, remember I told you that the hydrogen atom was a half an angstrom or 0.05 nanometers across. Well, this object you're looking at here is about 700 angstroms or 70 nanometers across and contains hundreds of thousands of atoms. And it's been reconstructed by cryo-electron microscopy. Feynman went on to talk about making tiny machines. He actually said, well, perhaps you can make machines like automobiles and just make them by having a machine make a machine that's smaller than itself, which then makes a machine that's smaller than itself, and so on. Well, we haven't quite realized that manufacturing capability yet, and as we'll discover in Chapter 10's biological machines work on actually fundamentally different principles because of the important role of fluctuations in systems that are that small. But you're looking here at the world's smallest motor. So the motor has a rotating piece that's a conductor between two electrodes in which the electric field is being oscillated so as to polarize the material and pull it or push it away from each of the poles. But the incredible thing is the armature on which this motor rests. So you can't really see it, but behind the motor and holding the rotating piece is a carbon nanotube. So here is the rotating part. Here is the carbon nanotube. And the carbon nanotube itself consists of multiple walls of carbon nanotubes. And because of the very smooth surface of the carbon nanotube, it's free to rotate like an axle on an almost perfect bearing, so that as the electric field is applied between these two pole pieces here, this whole object can rotate. To give you some idea of just how small this device is, the smallest carbon nanotubes at the center of this thing might have a dimension of about 2 nanometers across. This wonderful device was made in the lab of Alex Zettel at the University of California, Berkeley. Feynman talked also about making layered materials. If you don't like the properties of silicon, or germanium isn't good enough for you, or copper isn't good enough, well then why not put down one layer of, let's say, silicon atoms and then another layer of germanium atoms, and build up a material layer by layer by layer to have just the properties that you want. Well, this is done routinely today. The most common technique is called molecular beam epitaxy, and we will talk about this. The electron micrograph you see here, you see the scale bar here is 100 nanometers, and so these are layers of just a few nanometers thickness of mercury telluride and mercury cadmium telluride, and this whole thing then is put together to have unique and special properties as a detector based on growing the structure with molecular beam epitaxy. Feynman said, well, once we learn how to image and handle nanostructures, perhaps we can handle atoms. So perhaps we can do impossible chemistry by just taking atoms that otherwise we can't make react and pushing them together. These are scanning tunneling microscope images, and the two little features you see there are two atoms that are very close to one another, And in the second panel, they've been pushed on top of one another to form a molecule